Today's webinar will be about thermoelectrics, the basics more or less, and I will discuss the influence of temperature on electrical properties and how one can investigate those electrical properties with the instruments Linzais offers in the product lineup. So first of all, let me introduce myself. My name is Erika. I studied physics and I'm here at Linzais since 2020, and I'm here in the application lab responsible for service measurements and also test measurements, for example, if one is interested in an instrument. And my topic is more or less the thermoconductivity as well as the thermoelectric properties. Okay, so for those who do not know Linzais, just in short introduction, Linzais was founded in 1956 by Dr. Maximilian Linzais, who you can see here on the left image, in Seebeck in Bavaria, which is located in Germany. And we manufacture here in Seebeck instruments in thermal analysis. We have own sales and service locations in the US, China, India, and additionally, we have more than 65 distributors worldwide. So more or less in each country, there's a contact for our instruments. The most business area are really the measuring instruments for thermal analysis, thermoconductivity, and thermoelectrics. But as already mentioned, we also offer service measurements here in our lab, where we have a part of our instruments available. From history, we first started with such data loggers, but as the computer were more and more prominent, the company switched then to thermal analysis, which origin is here in Seebeck. The ceramics, porcelain are many companies located here. So this is why the thermal analysis in this field of application was very requested. And this is more or less the history of Linzais. Our product range is shown here on this slide. So it is ranging from the classical thermal analysis, so DSCs, TGAs, STAs, dilutometers. We also have instruments for thermomechanical analysis. A broad field we also offer is the thermoconductivity or thermodiffusivity property instrument. So additionally, we also offer thermoelectric materials characterization instruments, which is the topic today. And for special applications like thin film measurements, we also offer instruments as well as instruments for Hall effect. And what makes us unique is more or less that we offer a lot of different options and are open for customizations. So yeah, we build often unique tailor-made instruments to offer the best solution for the required application. Today's agenda will be first some general definitions of thermoelectric properties, like the Seebeck coefficient and the ZD. Then we will discuss the Linzais product lineup for thermoelectric property applications. And in the end, I will give some examples. So thermoelectricity in general describes the direct conversion of a temperature gradient into electricity and vice versa. So the thermoelectric effects are the Seebeck effect, its reversal effect, the Peltier effect, and also the Thomson effect. The direct conversion means that no conventional heat engine with moving parts, which typically need maintenance, is required. So this means that the thermoelectricity has a big potential for many kinds of everyday applications. Next to already established thermoelectric applications in, for example, the aerospace industry and laboratories, current hot topics are waste heat recovery from hot engines and combustion systems. And this could save billions of dollars if it could be captured and converted into electricity with thermoelectric devices. So with that, really the generated heat by the engines can be used for other applications. A recently topic as well is the Internet of Things, where remote devices like autark sensors and actors require autonomous power sources, or also one can use the thermoelectric effects for sensor materials, like it is shown here on the image on the lower right, where one can see a photo of the sample holder of an LFA, a laser flash analyzer. In the middle here is the thermocouple. The working principle of the thermocouple is also based on a thermoelectric effect. So thermoelectric phenomena, or also thermoelectric generators, if one talks about that, one typically talks about the use of the Seebeck effect. So as mentioned before, the Seebeck effect and the Peltier effect are more or less the same, just vice versa, simply said. And the Seebeck effect describes how a temperature difference along a conductor creates an electric field, and in consequence, the so-called thermal voltage. Simply explained, one can use such an illustration here. Here is a conductor. For example, a typical thermoelectric material is bismuth telluride. Here on the left, this material gets heated, and on the left side, it stays cool. On the right side, sorry. On the right side, it stays cool, and on the left side, it gets heated. Because of the introduced heat here on the left side, the charge carriers, or the cold charge carriers, can move back. And on average, this means that the charge carriers from the hot side diffuse to the cold side, until in consequence an electric field is built up, which acts against the movement. So the electric field is also shown here, and the size and the direction of the charge carriers of this hot side get then more energy and move faster to the cold side. The electric field depends also on the material and the temperature, which means that the Seebeck coefficient is a material-specific and also temperature-dependent parameter. The unit of the Seebeck coefficient is shown here. It's typically volt per Kelvin or microvolt per Kelvin. So these are the typical units for the Seebeck coefficient. And for the different kind of materials, metals typically have a small Seebeck coefficient, whereas semiconductors can have high Seebeck coefficients of several hundreds of microvolt per Kelvin, whereas the value for metals is typically a few microvolts per Kelvin. So yes, as mentioned, typically when one talks about the Seebeck coefficient, when talking about thermoelectric materials, and to be able to characterize the different materials and to choose the right one for different thermoelectric applications, one uses the so-called figure of merit. It is a quantity to characterize the performance of a device or a material, more or less, regarding the thermoelectric behavior, more or less. So the figure of merit is introduced, and it consists of the Seebeck coefficient, here squared, denoted by S, the electrical conductivity, the thermal conductivity, and the figure of merit is also dependent on the temperature. So these are the properties which are used to calculate the figure of merit. And the higher the figure of merit, the better, more or less, is the performance of the device. So this means that the aim is to maximize this figure of merit for a material or for a device to have the best performance. In detail, this means that one tries to use a high as possible Seebeck coefficient and a very high electrical conductivity, and tries to minimize the thermal conductivity here, so that here the figure of merit will be as high as possible. Yes. So typically, the CT value is determined by determining the single property, so the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. But generally, it is also possible to determine the figure of merit directly, for example, using a Harman add-on with our LSR. The Seebeck coefficient and electrical conductivity can be also measured with an LSR. The typical instrument which is used for thermal conductivity is the L of A, but here, just as a comment, I will go into detail a little bit later. The L of A measures firstly only the thermal diffusivity, which is here alpha, but the thermal diffusivity is directly connected to the thermal conductivity by the specific heat capacity and the density. So in practice, the conversion of heat into electricity is not performed by a single element, but by thermoelectric modules. So if many thermoelectric materials, these are typically called legs and are typically p-type and n-type combined, and these are interconnected thermally in parallel and electrically in line, and this connection is then called a module, which can be seen here also here in this illustrations. These modules can either be used for the conversion of heat into electricity. These are then called thermoelectric generators, or shortly TEG, or one can use the setup as a heat pump in order to create a heat flux. In this case, it is then called a Peltier element. Peltier elements are, for example, often used for temperature-sensitive applications like lasers or in laboratory environments, for example, in experimental setups. The thermoelectric conversion efficiency of a module can theoretically be calculated using the average CT values of the N and P-type legs, or practically measuring the electrical power output at a given thermal load. So then this part here or here, using the different figure of merits. And next to the maximization of the thermoelectric conversion efficiency, the material stability, costs, and toxicity, for example, are in the aim of research and quality control. And for this task, we have a comprehensive and advanced product lineup. and we are a partner of institutes, universities, and companies since more than 60 years and have a focus on thermoelectrics with the most innovative concepts since more than 10 years. And we try to offer instrument for different applications. So you can see here for the legs, one can use the typically LFA for thermoconductivity, LSR for electrical measurements. The LZT is a combination of LFA and LSR. One can use the HCS, the Hall characterization system, to find information about the Hall coefficient, and for thin film applications, one can use our thin film instruments. We also offer instruments for the characterization of the TEGs, so the modules itself, with our TEG tester, or regarding thermoconductivity, the LFA, for example. Here one can also determine the properties of the ceramics which are used itself. Our product lineup is now expanded with a new instrument. It's the LSR1. The LSR1 is a small instrument which offers the possibility to measure the electrical resistivity and the Seebeck coefficient for bulk material and thin films in the temperature range from room temperature to 200, and with an extension also down to minus 160 degrees Celsius. So as you can see here, we have a really broad product lineup for the field of thermoelectrics. We can measure bulk materials, thin films from cryogenic temperatures to 1,500 degrees Celsius. So for almost every application, we can find a solution. So in the next slides, I want to go a little bit more into detail regarding different instruments and which properties can be measured. So yes, the first step of developing a high efficient thermoelectric generator is to look for good thermoelectric materials with a large Seebeck coefficient and electric conductivity and a low thermal conductivity. This can be seen here from the formula for the figure of merit. And the single parameters, of course, need to be characterized in the temperature range of interest of the plant application. The main instruments which are used for the characterization of the figure of merit of a thermoelectric material are the LFA and the LSR. The LFA measures the thermal transport properties, so the thermal conductivity more or less indirectly. The laser flash method is a standardized technique which uses a light source. It is either a xenon lamp or a laser. And this power source shoots a short high energy pulse to one side of the sample. The sample absorbs the energy, and a part of the energy is also emitted on the rear side of the sample. And this infrared radiation is collected by an infrared detector. So in the end, one obtains a temperature rise curve with time, which looks similar to this one here. From this curve, one can then calculate or determine the thermal diffusivity, which is denoted here by alpha. If one then also has information about specific heat capacity and density, one can calculate the thermal conductivity, and thus the first property of the figure of merit is determined. Additionally, the LFA offers the possibility to measure also CP by a comparative method, so that here from this formula already two properties are determined. The big advantage of the LFA of this method is that one can cover a lot of different applications. One can cover a broad temperature range from cryogenic temperatures up to even 2,800 degrees Celsius. It is possible to measure bulk materials as well as micrometer thick films. And additionally, one can measure low thermoconductive materials to very high conductive materials, like generally said, diamonds. So the LFA is the most universal instrument for thermoconductivity determination. We also offer different instruments for thermoconductivity measurements. But the LFA, as mentioned, is the most universal one. For thermoconductivity determination, we also have some webinars online where you can get more information about the product line regarding this product, this property. And the only disadvantage, more or less, of the LFA, as already mentioned, is that the thermoconductivity, unfortunately, cannot be measured directly, but we first determine only the thermal diffusivity. But with the comparative method, CP can be determined, or one can determine the CP, the specific heat capacity, by, for example, DSC, a calorimeter. And the second main platform used for ZT measurements is the LSR, which stands for Lin size, Seebeck, and resistivity instrument. With this instrument, one can determine the Seebeck coefficient and the electrical resistivity, thus also the thermal conductivity. And for the Seebeck coefficient measurement, the setup schematically looks like that. So the sample is clamped in between two electrodes. The electrodes also can have additional, or the lower one has an additional gradient heater here, so that one can apply a temperature gradient onto the sample. From the side, the sample is contacted with two thermocouples. Those two thermocouples, on the one hand, measure the temperature difference on the sample due to the temperature gradient, and additionally, they also measure the generated thermal voltage. And with these two informations, one can then calculate the Seebeck coefficient. The same setup is also used for the resistivity measurement, which means that with the LSR, the classical LSR, the LSR3, one can determine the resistivity and also the Seebeck coefficient in one run. For the resistivity measurement, we use a DC-4 terminal measurement technique, and we impress a constant current, which is called here IDC, into the sample using those two electrodes here, and the resulting voltage drop over the portion of length T is measured using the thermocouples, which touch the sample from the side. So here the voltage drop is measured as well. And these are then the properties needed for the electrical resistivity determination. Additionally, one needs the cross-sectional area of the sample, so one needs to know the geometry of the sample. So in summary, the LSR can be used to characterize a broad range of samples, from typically bar-shaped legs to also round discs. But this can be also used then for an LFA measurement. So one just has to prepare one sample to measure all properties. Additionally, the LSR platform can be equipped with a low temperature furnace. So one can also realize cryogenic temperatures, or we also have different furnaces for high temperature applications with different heating and cooling rates. So if one requires high heating rates and a fast heating or fast cooling, this can be realized as well, up to 1500 degrees Celsius. Additionally, we offer solutions for measuring high resistance samples so that high resistive materials can be characterized as well. And as mentioned before, one needs here the distance of the thermocouples, so the portion of length which is used for resistivity measurement. To be able to determine the distance of those two thermocouples as precise as possible, there is also a camera option available so that the resistivity measurement will be as precise as possible. There are also various materials available for the electrodes and thermocouples. So the standard ones are, for example, typically platinum electrodes and thermocouples. But if one knows that there will be a reaction, and depending on the temperature range, one can also use type K electrodes and thermocouples. So there are also various options to customize the LSR. Additionally, what can be done as well with some limitations, more or less, is the Harman adapter, so that one is able to characterize the figure of merit directly. So with the Harman add-on, one can directly measure the figure of merit with the LSR. The Harman measurement current is immersed into the sample with two needle contacts, which is shown here. And due to the Peltier effect, then one of the transitions is locally cooled or heated. And by that, a temperature profile is established. And if one uses then the ratio of the measurement of the initial voltage drop, so the ohmic part without a temperature gradient, and the measurement of the stationary voltage drop, so the one including the thermal voltage, if one uses these two measurements, one can calculate directly the figure of merit. So with the Harman method, the advantage, of course, is that one has the figure of merit directly, and by that the measurement error is smaller because one measures it directly and not multiplicates the errors of the different single measurements of Seebeck coefficient, electrical conductivity, and thermal conductivity. Of course, here typically the measurement error will be higher compared to a direct measurement. The disadvantage and also the limit of the Harman method are that it only works for good thermoelectric materials, and the temperature range is limited to about 300 or 400 degrees Celsius. The product lineup of LFA and LSR is more or less rounded off by the integrated LZT platform, which is simply said a combination of an LFA with a laser source and the LSR in one. So by that, one has a powerful tool to save costs and also lab space, to measure the figure of merit just with one instrument. And this setup is ideal for the research community, where it's not that important to have a high sample throughput. So here one can only measure with the LCT one sample at one in one run, where with the LFA, for example, one can measure up to 6 samples at the same time. And in addition to the commonly used characterization techniques, we also offer another product line which perfectly matches the needs of thermoelectric material investigations with our HCS, which stands for Hall Characterization System. We offer the possibility to measure the Hall constant with a high accuracy. The Hall constant can be used to calculate the charge carrier density and the Hall mobilities. In addition, the sign of the Hall voltage indicates also the type of majority charge carriers. Here, a negative sign indicates electrons and a positive sign the holes. The knowledge of the charge carrier concentration is very important for the research on thermoelectric materials, as the figure of merit value strongly depends on it, which can be seen here in this diagram. So here for the carrier concentration of a few 10 to 19 per centimeter cube, one has the highest figure of merit for this type of material. For the HCS, we offer 3 different units with either 2 permanent magnets or a more powerful electromagnet or with a rotating Hallbach magnet, which allows then oscillating magnetic fields. And these systems are all equipped with an integrated and optimized measurement electronics and can be upgraded for high temperature measurements up to 700 degrees Celsius, as well as, for example, lock-in amplifiers for noise-reduced AC measurements. And another very important and also hot topic in the field of thermoelectrics is the investigation of nanostructures, so thin films, because these thin films or nanostructures can possess some very unique features, which are advantages for the thermoelectric application. On the one hand, additional charge carriers and phonon scattering within thin films or nanowires can also increase the ZT value by suppressing lattice thermoconductivity or increasing the power factor. On the other hand, the production costs can be reduced because thin films simply need less material and can easily be scaled up. So it is also known that thin films have different properties compared to the bulk material. So it's very important to also characterize the thin films itself and do not just use the properties of the bulk material. For these applications, we offer 2 different systems, which are especially dedicated for the characterization of thin films. On the one hand, it is the thin film laser flash analyzer, which measures the cross-grain thermal diffusivity of thin films from the nanometer to the micrometer range and works with a, let's say, similar method as the classical laser flash analyzer, which I showed some slides before. The second instrument for the thin film analysis is the TFA. The TFA is the world's only integrated system, which allows a comprehensive characterization of thin films in plane. And it offers the possibility to realize a complete analysis. So it can measure the Seebeck coefficient, the electrical resistivity, thermoconductivity, specific heat capacity, and the Hall constant for nanometer to micrometer thin films. So with the TFA, a full analysis can be realized. So these were up to now the instruments for the characterization of the thermoelectric materials itself. And the next stage would be to investigate the finally developed and assembled module, the TEG. For this, we offer our so-called TEG tester, so thermoelectric generator tester, which is a device which can measure the conversion efficiency of modules under real-world conditions, more or less. So for the measurement, a variable heat flux can be applied to the module under defined conditions like contact pressure or different temperatures. And in addition, the corresponding output voltage can drive a variable load. And this procedure is then called the maximum power point tracking and is a commonly used technique to characterize the real performance of energy generators. And next to the conversion efficiency, the TEG tester can also be used as a thermal interface tester. In this configuration, it is then called TIM tester, so thermal interface material tester. With this method, one can then, for example, analyze the thermal conductivity and the thermal impedance of the contact passes, which are used for optimizing the thermal contact at the top and the bottom ceramics to the thermal elements, for example. And for more or less the same topic at DSC, it is a differential scanning calorimeter, can be used to determine aging effects under temperature influence. For example, for this contact passes which are used. And in addition, a DSC is the most commonly used instrument for the determination of specific heat capacity. The specific heat capacity, as already mentioned, is required for the thermal conductivity determination if one uses a laser flash analyzer so that the thermal conductivity can be calculated using the CP, the thermal diffusivity, and the density. And in the case here of such a module, the LFA can also be used for the ceramic plates, as already mentioned, and can also be used for the complete module thermal conductivity or thermal diffusivity determination. On this slide, some thermoelectric materials, typical thermoelectric materials are presented. So one tries to have a material with a large Seebeck coefficient and a high electrical conductivity and a low as possible thermal conductivity. The most promising thermoelectric materials can be found in the groups of semiconductors and semimetals, and this is due to the band structure. So on the picture here on the right, one can also see again that the figure of merit also depends here on the carrier concentration. The carrier concentration can be determined using an HCS. The aim is to optimize these materials in order to increase the power factor. This is how the numerator here is called, and reduce the thermal conductivity, as already mentioned. So for this, many different approaches, like, for example, alloying or the implementation of additional scattering sources in form of, for example, nanoparticles, superlattices, or composites have been investigated and developed. On the left here, some thermoelectric materials are shown with their performance evaluation and dependence on temperature. So for example, one can see here the commonly used bismuth telluride, which shows here the figure of merit independence on temperature, as well as some alloys of bismuth tellurides. One can see zinc selenide here in orange, or silicon germanium here in red to brownish color. And one can see here clearly that different materials have different figure of merits, and the figure of merit strongly depend on the temperature. So, coming now more or less to the end. In the end, I want to show you some application examples measured by our instruments. Here on the top, one can see a silicon germanium alloy, which is a typically used material in electronics. The silicon germanium alloys are high temperature stable thermoelectric materials and thus are often used under challenging environmental conditions, like, for example, space missions or high temperature waste heat recovery. The LSR here measured a new developed alloy, and the measurement was performed from room temperature or about 50 degrees Celsius to 270 degrees Celsius. And here one can clearly see that the material shows an increasing resistivity. The absolute Seebeck coefficient was measured at the same time and shows first a slight increase of the values and then the values decrease with increasing temperature. As I already mentioned, with the Harman method, it is possible to directly determine the figure of merit with the LSR. Here on the right, one can see an example for a bismuth telluride sample. And here one can see the voltage measured applying a current on a thermoelectric material. So one has here the ohmic drop and the thermal voltage shown here on this diagram, and dividing one by the other gives then the figure of merit. So this bismuth telluride sample, it is a NIST certified material. We use it as a reference material, and here one can see the typical voltage distribution at a single temperature measurement point. In this case, the figure of merit value was recorded at room temperature. And here one can see that the figure of merit was determined to be about 0.5, which is the literature value for bismuth telluride at room temperature. Here are some examples for the TFA analysis, so a thin film measurement. As already mentioned, typically thin layers show different properties. So typically show lower thermal conductivities, while the electrical conductivity and the Seebeck coefficient are much less affected, resulting in higher ZT values in total. On the left, bismuth antimonides with various chemical compositions, or in general, bismuth antimonides with different chemical compositions are well-known semiconducting thermoelectric materials. Here, an example is shown of an 84 nanometer thick bismuth antimony layer, and here one can see that the measurement was performed in a temperature range of 120 to 400 Kelvin, and this thin film was prepared by a thermal evaporation. And one can see here that in one run, one could get the thermal conductivity in purple, the electrical conductivity in blue, as well as the Seebeck coefficient. And based on that, then the figure of merit here in orange was calculated, and the material is fully analyzed here with the TFA. On the right, one can see an analysis of a 50 micrometer thick P.PSS layer. P.PSS is a typical example for an organic conductor and thermoelectric material. Here again, a full analysis was performed, and The electrical conductivity, thermal conductivity, and the Seebeck coefficient were measured here in the similar temperature range from 110 Kelvin to 350 Kelvin. The sample here was prepared by drop casting, and one can see here then the resulting figure of merit in comparison to the bismuth antimonite sample. The values are much lower. And here, the last application example is shown. Here, the analysis was performed by an LFA, a DSC, and the others are here bismuth selenide samples and bismuth antimony samples, so N-type and P-type samples were characterized. The thermal diffusivity was measured with an LFA, and the same sample was used to be measured with an LSR to determine electrical resistivity and the Seebeck coefficient. With a DSC, the specific heat capacity was determined. Using all those values, one can first, or using those top values here, one can first determine the thermal conductivity. With the thermal conductivity and the electrical properties, one can then determine the figure of merit, where one can clearly see that the P-type sample has, at the lower temperatures, a higher figure of merit, whereas at the higher temperatures, the N-type and the P-type show a similar performance. Okay, so this was first all from my side. I want to thank you for your attention. In summary, I showed you different instruments which can be used for the characterization of thermoelectric materials, for bulk materials, thin films, also for the TEGs, the complete module. One can also use different instruments for just the characterization of the legs. And we offer a broad product lineup for different temperature ranges, for different conductivities, different thicknesses, and different properties. So again, thank you for your attention. And now I will answer your questions. So if you have any questions, just type them into the chat and I will answer them. Now, so during the talk, there was the first question. So I presented to you, let me go to the slide. It was here. I presented to you our new instrument, the LSR1, which is a tabletop instrument. It is rather small. It was asked what is the size of it. So it's like, what is it, 40 times 20 centimeters. I do not know the exact size of it. I have to look it up. But it's a rather small instrument. Here on the front, there's an additional sensor, which is similar to the Hall characterization system sensor. So there's a circuit board where you place directly the sample on top of it and you contact it there. So there is also the gradient heater built in onto this sensor, and the sensor is then put in here into this instrument for the measurements. So yes, the next question was, what are good thermal conductive materials for the Harman part? So it means that the resistance should be not too high. So as mentioned, we also have a option for high resistive samples. So the resistance of the sample should be rather low and show good thermoelectric properties. So should not be that insulating, and these are only suitable then for the Harman method with the LSR. For example, our reference material here is bismuth telluride. So in the range of the bismuth telluride properties, we can use the Harman method. The next question was the TG or TIM tester, if it's only for measurement of vertical geometry or also for planar TG geometries. I'm not sure if I understand that question correctly. So the TEG tester is an instrument where you put in such an TEG directly between two meter bars. So the temperature gradient will be applied from the top to the bottom. And you use such more or less flat TEGs with ceramics on top and the bottom for the TEG tester. Our next question was, what is the absolute Seebeck coefficient? I mentioned it. Where was it? Yeah, I do not know which slide I mentioned it, but what is meant with absolute Seebeck coefficient is that first what we measure with the LSR is the relative Seebeck coefficient, as the electrodes here of the and the thermocouples of the LSR also show a Seebeck effect. One needs to calculate that, and this is done in the evaluation software then here with our system. So one more or less subtracts the influence of the effect of the electrodes and thermocouples onto the material, and by that one gets then the absolute Seebeck coefficient. Okay, so yes, these were here a new question popped up. There is a question if it's possible to estimate the carrier density of conducting polymers with our HCS. So it depends on the properties. So all of the just mentioned instruments are very good described on our website, where also the measurement range is given. So there one can check if the properties fit into the given range of the specs. I just cannot answer you the exact numbers, which is the range for the Hall coefficient. So this I need to look up. But as mentioned on our website, everything is described very detailed so that you can have a look. Let me see if I can find that. Yeah, so the carrier concentration for the HCS, which is given on our website, is 10 to 7 up to 10 to 21 per centimeter cubed. So this is the carrier concentration range, which can be determined with the HCS. And there's a specific question regarding the LSR3, how it can be calibrated. The LSR in general is an absolute measurement method. So it's not calibrated directly. What we typically do, we have a constant hand reference material, which we use to measure with the LSR in a defined temperature range with specific settings. And we also then have the possibility to evaluate it, and we have given ranges in which the determined value should be in. And based on that, one can find out if the system works properly, or if, for example, the electrodes needs to be cleaned or something does not work. So the LSR is not calibrated, but just cross-checked with a well-known reference. Okay, so these are all questions for now in the chat. If there are any further, you now have the possibility to ask that. Otherwise, you can just also contact us. Our contact email address is given here. So if you have any further questions, you can also just contact us by mail, for example. The address is info@linsize.de. So yes, as mentioned, again, thank you for your attention.